Hey everyone, so this is one of my follow-up videos. If people don't know, what I've gone into the habit of is doing a follow-up video to like my main videos where I can talk about your comments and questions and show you things that I didn't talk about. This is a follow-up video to the birthday magic square video, which I hope you enjoyed, I hope you had fun with. I should emphasize though that I am recording this as live, okay, so I'll just be talking into my webcam here, and then I talk live with all the ums and ers and the swallowing like that, with the purpose that it makes my life a bit easier, so I don't have to edit so much at the end. So what I'll be doing is showing you things that I cut out from like the main video I made, things I wanted to talk about, but I'll be doing that just by like holding up pieces of paper at you. I mean, no graphics or anything like that. Just makes my life a bit easier. I hope you did like the birthday magic square video. Just to remind you then what that was, it was how to make magic squares like this, where you have like someone's birth date in the top row. I was using Leonard Euler's birth date in the top row, and then your birth date adds up to your special birthday number. If you add that up, the special birthday number was 43, and then every row adds up to 43, every column adds up to 43, the two main diagonals add up to 43, and then there was a whole bunch of other magic things. The four numbers in the middle add up to 43, the four corners add up to 43, the quadrants, top left, top right, bottom left, bottom right, add up to 43 as well. The broken diagonals, which I said were these two numbers and these two numbers, or these two numbers here and these two numbers here, they add up to 43 as well. There were other things that I didn't talk about, other magic properties like corners of a 3x3 square add up to the magic number. So 15, 17, 3 and 8 will add up to that special number too. There are other groups of 4 that do add up, like this group of 4 will add up here. So the 4, 17, the 6 and the 14. But on the other hand, there are some groups that don't add up to the magic number. So this group here doesn't add up. And I might talk about how we could alter this so that all the groups add up. We'll come to that. We'll come to that. So I said, this is how you can make one of these. You can make them for your friends and family, make them for yourself, of course. How incurious would you be if you didn't make one for yourself? And people did seem to enjoy them. They were giving me comments like, oh, I'm going to make this for my brothers and my sisters and so on. I've got actually a comment here from Soren, who is a maths teacher, who gave me a comment that I did enjoy, who said, I don't know whether to bless you or curse you. I'm a maths teacher, 6th to 9th graders, and after I had watched your video, one of my pupils had her birthday, so I drew her a square for her. Q today, where another one has a birthday and immediately asked for her square. It seems that I am doomed to draw a square for each of my pupils in the class from now on. But at least they are excited about something relating to maths. That's the point. That is the idea. So it is just for fun, but it's all about sparking some curiosity, right? And once you started sparking some curiosity, then hopefully you can enjoy other mathematical things later on. So let's talk about some of the things that I missed out from that main video, and then maybe at the end I'll tell you some of the other projects I'm working on. Right, so the whole point of it was teaching you how to make an Euler square, which looks like this. This is an Euler square. I described it as kind of like a Sudoku sort of thing. So every row and every column and the two main diagonals contain A, B, C, D and 1, 2, 3, 4 without repeats. So that's what I've got here. A, B, C, D, 1, 2, 3, 4, all contained in this Euler square. I'll tell you what happened was I was actually preparing like a thing for teachers, and I said, oh, I'll do a thing about Euler squares because they're kind of fun, because they're a bit like Sudoku. You can give them to kids as a kind of Sudoku puzzle, a bit of a logic problem, and they can sort of fill them in. And you don't have to use letters and numbers like this, right? You can use like shapes and colours, or colours and colours, or other things. And I was saying this to the teachers, and I said, oh, you could use letters and numbers, and it would look like this. And I looked at that, and then I realised, Oh, Euler squares are magic squares. Because automatically, just how they're designed, how they're built, every row is going to have the same total. Every column is going to have the same total. The diagonals are going to have the same total. I only just realised that. I mean, I should have known that. Because I know Euler squares and I know magic squares. And I you kind of see that they're related. It's something about all the rows being, the same. But I hadn't made the connection. It wasn't a new connection. Obviously, this goes back to Euler. Probably goes back further. But Euler was investigating magic squares, actually, and then came up with this method for doing it. And so, yeah, it's well known. If you Wikipedia this stuff, there's a whole section about Euler squares and magic squares. It's well known, but not everyone knows it. And someone like me who does talk about silly maths, I didn't know it. I've got a book on my shelf all about how to construct magic squares. I mean, a whole book, and it's all about, to construct magic squares of all these different sizes, and you use night moves and diagonal moves, and then you shift it like this and do this. Full book of how to make them. I looked again to see, had I just forgotten that it teaches me about Euler squares? It doesn't even mention Euler squares. It did mention Euler squares. One sentence. It said, or you could do it with an Euler square. And that was it. And so I think there are people who know maths and may not have made that connection either. So that's why I wanted to make the video. All right, Euler squares are magic squares. That was the revelation. One of the things I didn't put into my video then is, here's a nice choice for A, B, C and D. What about this? So I'm going to choose A is 0, B is 4, C is 8 and D is 12. What that's going to do is that's going to fill this in with consecutive numbers. So the A squares are going to be 1, 2, 3, 4. The B squares are 5, 6, 7 and 8. C is then what? 9, I guess. Where's 9? 9, 10, 11, 12. 9, 10, 11 and 12. And the D squares are going to be 13, 14, 15 and 16. So it fills it in with the consecutive numbers 1 to 16 with all those magic properties of the Euler square. So automatically rows, columns, diagonals and things like those corners and quadrants and things. So that's a nice one, because that's kind of traditionally how you do make a magic square with consecutive numbers. That is a nice one, and you can, remember, fill these in with any numbers you want. But what this does prove is that if your birthday total is less than 34, then you're going to have repeats, or you're going to have negative numbers. So if you fill in a magic square with consecutive numbers 1 to 16, the magic total is 34. You can prove that. It has to be. This is me proving it, right? If you add up 1 to 16, that's 136, right? But 136 has to be equal to adding the 4 rows together. So each row has a magic total of t. So that's a total of t, t, t and t. So 4 lots of t needs to add up to 136, which proves that t has to be 34. So there's no other choices for that. So the magic total is 34. Okay. So if your magic total is less than 34, which might be true when you're doing these birthday magic squares, then you can't use the consecutive values 1 to 16. You're going to have to use smaller values, which means you go into negative numbers, or you use some repeated 1s and 2s and 3s and 4s, like something like that. So you're either going to have repeats or you're going to have negative numbers. Not forgetting that you might have repeats in the birth date that you're using as well, which you can't avoid either. Now I know some people don't like that. Some people really struggled with that. Well, what about repeats? Negative numbers. I'm afraid just for some of these birth dates it is unavoidable. Nothing you can do about it. So you just have to accept it. Just enjoy it. Yeah, what's wrong with negative numbers? Nothing. Nothing's wrong with negative numbers. I would prefer negative numbers to repeats if it was me. And I think you can always avoid repeats. I'll try and convince you of that later. But if you look up magic squares on the internet, which is what I did next, I went, I see Euler squares are magic squares. So I looked them up, And I typed in birthday magic squares, that's typing. Typed in birthday magic squares into Google, and this is what I saw. This is almost exclusively what I saw if I Googled it. And it was this. And it said, how to make a birthday magic square. And it gave you this square. And there you go. That's done in the format of date, month, century, year. So if you've got your date, month, century, year, and you put that in the top row, and this tells you how to fill in the rest. And that's got like year +1, century -1, month -3, D +3, and the rest. And that's what it tells you to do. Almost entirely, that's what it is on the internet. And I know why that's the description on the internet. Well, also because it's kind of nice, isn't it, to do it with the date, month, century, year. I mean, that is more sort of friendly, approachable way of writing it out. But I don't like it. And there's a reason I didn't teach you to do it this way. Because it's hiding the structure of the Euler square. And now that it's hiding the structure of the Euler square, you don't know where it's come from, you don't know how it was made, and you can't change it. So you don't understand it, you can't change it. So now if you do get negative numbers, which you probably will, look at this month -3 here. If you do get negative numbers, then yeah, you have no idea how to change this into a different kind of birthday magic square. Now there is a reason why that story though keeps coming up on the internet. It's because that was the approach used by Ramanujan, famous Indian mathematician, and in his notebooks he made himself a birthday magic square. What a nerd. He made himself a birthday magic square, and this is his birth date. It was 22 December 1887. There's his birthday magic square that he made for himself. And then someone's, I think this is what was in his notebook, and then someone's gone, oh, and that's the structure of what he's did. And then they put that all over the internet, and people have copied that on the internet as well. That is an Euler square. It does have the structure of an Euler square. You write it in the form of an Euler square, it looks like that instead. So he's not done 1, 2, 3, 4 on the top row. It's gone 1, 4, 3, 2. Because he's adapted it, right? He's adapted it so it works better for his birth date. He's done something different to me as well. This is an alternative version of the Euler square because I filled in the Euler square, and then for A, I put A in the third square on the second row. He's put A in the fourth square on the second row, and everything else is then filled in and forced on you. It's just a different choice he made there. So that's just a variant there, an alternative Euler square. But it's still, he used an Euler square to make his birthday magic square. But that's what you'll see on the internet. Like I said, I don't like it because it's hiding. That's why I didn't want to teach you, because it's hiding that structure. So now you don't understand it, you can't adapt it and things. But the most common question I was getting was, but what about repeats? People go, oh yeah, but what about if your birth date was 1st of January 2001? That came up a lot, things like that. So let's talk about repeats. I think you can always avoid repeats, at least if you allow negative numbers. So let's take the most extreme example of this. And I'm going to use this. Let's just say it was all equal. That's not a birth date, is it? But let's just say, oh, all these numbers are equal as a real extreme example of this. I'm going 6, 6, 6, 6. Now I want to fill this in without adding any more extra repeats. I can't avoid those. Those are fixed. That's part of what I'm doing. But now I don't want any more repeats in the rest of the squares. Now I can choose those values that I put in my Euler square. I was showing you 1, 2, 3, 4, because obviously that's the most natural thing to put in. But if you play around with it, I've gotten quite good at playing around with it. Yeah, I mean, I'm not quite good enough to perform it on a stage. I can do 1, 2, 3, 4 on a stage, but perform it if I have to invent some other numbers to avoid repeats and things live. I can do it for someone in a pub or somewhere, something like that, if you give me a second to think about it. So I've been playing with this. 1, 2, 4, 8 as my choice of numbers seems to be quite good, especially in some extreme like this. So let's do it. Let's try this out. So 1, 2, 4, 8. Really, when I'm filling these in, I've memorized the patterns of A, B, C's and D's. So let's do A's. This is A, then this is A, then A's here and A's here. It's like a night move, then a diagonal, and it kind of bounces off that and does a night move down here. So that's how I'm memorizing it. So that's the pattern of A's. And then you follow these numbers. Actually, you do the differences. You don't even have to worry about what is the value of A, B, C, and D. Just think about the differences. This is increasing by 1, increasing by 2, and increasing by 4. And that's how I'm doing it. So I increase by 1. I increase by another 2. So that's going to be 9. See how I'm doing it? And then it's increasing by 4. So that's going to be a 13. That's what I've memorized. If you want to know how I'm performing it live when I do it in front of someone, yeah, I can pretty much do it like that. I actually do the D's next, which start from this corner and decrease in the same pattern but symmetric. So it's night move, diagonal, night move, but decreasing order. So I'm going to go decrease of 4, decrease of 2, decrease of 1. So that's going to be a 2. Then it's a decrease of 2 for 0 and a decrease of 1. So yeah, there is going to be a -1 there. But that's not a surprise because that magic total is 24, which is less than 34. So repeats or negatives, you're going to have to accept one of those. I will do the B's next, and that goes increasing order. And it actually starts from that. So it actually increases with a night move. I do a diagonal, and I see it as a wraparound. I go up and wrap up to the bottom and the left. So that's my diagonal. And then I do a night move. And it's in increasing order, starting from here. So I have to increase to 1, an increase of 1, 5 to 6, then an increase of 2, which is 8, and then an increase of 4, which is 12. And this is how I'm doing it. And then the C squares start from there, and they're in decreasing order. They're going down. So I'm going down by 4 to get to there, down by 2. I call that a diagonal, which is there. And then a night move to there, which is a decrease of 1. I'll do it for you. So I'm decreasing by 4, 10 to 6. Then I decrease by 2. That's going to be a 4. And then I decrease by 1, 3. There. And I've done it. And I've done it without repeats. That was the point. There are no repeats there. I do have a negative, but no extra repeats in the rest of it. And I have all my magic properties. Rows, columns, corners, etc. All add up to the magic total here is 24. So yeah, you can do it. If I can do it in that extreme example, I'm pretty sure I can always do it. And I will try and convince you better than that. But I'm pretty sure you can always do it. But what about the birthday that a lot of people were wondering about? They go, well, okay then, what about, 1st of January 2001? I'm going to use 1248. Actually, I'm going to do 1284 because I can. I'm allowed to do that. And I'm going to do 8 there as the biggest number on the 20. That means the 20 values will now have to decrease. So I guess that will just make the numbers more sort of closer together, which maybe makes a nicer square. Same idea though. This is my pattern of A's. And then I follow this, these differences. I increase by 1, I increase by 6, and then I will decrease by 4. And that's why I'll fill in the A squares, B, C's, and D's like that. This is what it looks like. And yes, you can do it. There it is, without repeats. 1st of January 2001, filled in, but with negative numbers. Not a surprise, because the birthday total there is 23. So yeah, that's going to be negative numbers. So some negative numbers there, but no repeats. And that's with 1, 2, 8, and 4. I have gotten good at this with a bit of practice. So you can, and it's done by observation, by the way. I haven't got a method yet that isn't just obviously I can obviously repeat. I can obviously avoid some repeats. I can avoid some obvious repeats. That's the French. That's the sentence I was trying to say. I told you it was live. So I can obviously avoid, some repeats. Never mind. I'll abandon that sentence. But yeah, it is by observation. So I'm just like looking at the numbers. Sometimes I go, oh, now I've messed it up. I haven't avoided the repeats at all. Now, the most generic version of making one of these squares will look like this. Where I've gone like a plus w, b plus x, c plus I, and d plus z, where w, x, y, and z could be any numbers I want, and they can be, you know, they don't have to be in increasing order or decreasing order or anything like that. So w, x, y, and z could be in any order I want. So that is the most generic version of this Euler square. But there is another way of writing one of these squares. It looks like this. So imagine I took this generic Euler square, and instead of w, x, y, and z, I filled this in and I had w, x, y, and z equal to 0, right? So I'm going to set those numbers to 0. If I do that, then what I'm going to get here is like A, B, C, D, and all these are going to be A, B, C, and D, which looks like this, although I've actually written this with the date, month, century, year version of it. So date, month, century, year, and then every row is going to be date, month, century, year, but in a different order, like the Euler square. So that is an Euler square, and that has all that magic as well. It has all the same properties. All the rows are going to equal to the magic total, the columns, the diagonals, and like the quadrants and all that stuff. It's all still there, but I'm going to have loads of repeats this time. Repeats, repeats, repeats. Every row is going to be full of repeats. And, you know, it's worth looking at that as well, because it does show that I can definitely do every birthday magic square without negative numbers if I want to, but I would have repeats. And I reckon that I can do every birthday magic square without repeats, but it might include negative numbers. It doesn't have to, but it might include negative numbers. It's just, you can't have both. You can't have everything. So that's me putting w, x, y, z to 0. That's what you get. Now, I could do this. I could then add on base elements. I'm calling them base elements, which are these 4 magic squares. So these are 4 magic squares, and these are where I've set here w to equal 1, and all the other numbers are set to 0. And that's what I would get. That's kind of a birthday magic square as well. I've set the top row to be 0. 0, 0, 0, 0 in the top row. I've done the Euler square thing. This is what I've got. Here's the other base element here. I've got 0, 1, 0, 0. So I'm setting x to 1. That's what I would get. This is me setting y to 1. This is what I get. And this is me setting z to 1. This is what I get. And the top row is set to 0, 0, 0. If I want to make the generic version, this version here, then all I'm doing is starting with this square. Use this as your starting point, your starting square, and you're adding combinations of these base elements. So if I wanted to add 1, 2, 3, 4 as my w, x, y, and z, I would add 1 copy of that, 2 copies of that, 3 copies of that, and 4 copies of that. By adding, I mean you're adding the corresponding cells. So top lefts would all get added together, right? The second square in the first row would all get added together. That's how you do the adding. So these are your base elements. For example, then, this is me doing 1, 2, 3, 4. That's your starting square. That's me doing 1, 2, 3, 4, which was 1 copy of the first base element, 2 copies of the second, 3 copies of the third, 4 copies of the fourth. That's what I've got. Zeros in the top row. That's what I've got. If I want to do a 1, 2, 3, 4 Euler square, I'm adding those 2 things together. So you could think of it in that way. It's all I'm saying. Yeah, other combinations is done the same way. So if I wanted to do the 1, 2, 4, 8 magic square, this is what you get. So there's zeros in the top row, 1 copy of my base element, 2 copies of the second base element, 4 copies of the third, 8 copies of the fourth base element. That's what I've got now. This is what I would add to this starting square. Here's the thing about this one. There are no repeats here. So even if you have repeats here, anything that's repeated, they're not going to be repeated once I've added these. They're going to become different. So adding this would make repeat values different. If I did my 6, 6, 6, 6, here in the top row, these would all be 6s, but they weren't when I did it because this makes them all different. I'm afraid that's not enough to solve everything, because once you've added that, you might find 2 values that were different are now the same. So you go, oh, so you might just be in the similar position you were before. You could add that again. Just add another copy of it and then try and make those different. Eventually, this is going to work. Eventually, this is going to make all your values different. So yeah, I reckon you can make all your values different. I mean, the extreme of that is, imagine if I just filled in one of these birthday magic squares with like 2-digit numbers in the top row. Let's just keep it to that, like 2-digit numbers less than 100. I could keep adding this. Maybe if I did it 100 times, this is what you'd get. Effectively, you've got W, X, Y, and Z being 100, 200, 400, and 800. Zeros in the top row. That's like doing this 100 times. This is what you've got. You've got 400 here, minus 400, 100, minus 100. But if you added that, yeah, you're definitely going to make everything different with that. Although it's not going to look great, but it can be done in principle. I think you can do better than that, though. I think you can always make your birthday magic square have non-repeating values and not use something as extreme as that. So here's a challenge for you. As I was playing around with these things, this is one that I found particularly difficult. It was just a random date. I was just playing with some random dates. So 16th of December, 1612, 2021. I was just playing with some random dates and I found that one particularly difficult. So here's my challenge to you. Can you find a W, X, Y, and Z so that that is filled in without repeats? It can be done, but I just found that one particularly difficult. But it's not huge values because this is something we've discovered. So I asked a friend of mine, Christian Lawson-Perfect, asked my friend Christian to make me a birthday square generating webpage for you so that you can play with birthday magic squares without going through all this hassle. So yeah, my friend did that. Let me show you. Actually, I'm going to use OBS here. I should be able to switch over. Hopefully I can. Great. So I can switch over and this is it. Yeah, so this is what Christian has made for me. And there's the Earl there. I'll put the link in the description. You should be able to see the link there at the top. Something or other whatever.com/birthday-magic-square. Yeah, I'll put the link in the description, but you've got it there. So this is what Christian's made for me. And we can put any date we want in this generator. Let's pick a random date, 24th of April 1842. Right, I am ready for my birthday present. 87 is the magic total. Okay, and this is showing you a birthday magic square generated and it shouldn't have any repeats. So yeah, we can do this without repeats. And Christian has checked this, any valid date can be done without repeats. So you should have no repeats there, and we've made it the way I've just described it by having a starting square, which is just date, month, century, year, that thing, and then adding on combinations of those base elements. And by adding combinations of those base elements, eventually you can get something that without repeat, and Christian reckons he can do any valid date and the coefficients of the base elements can be less than 10, from 0 to 10, 0, 1, 2, 3, 4, up to 10. So yeah, looks like you can do it. But I don't have any like systematic way of doing it. I should say this as well, switch back. I was talking about base elements before because I was saying that this is my base elements. So you add combinations of these. I should point out though, if I add all 4 of those together, they all cancel out. If I add 4 of those, I'll just get 0, 0, 0, 0 everywhere. They added together cancel out, which shows that I could write one of them in terms of the other 3, which shows that actually I can do any of these birthday magic squares with 3 of these elements, 3 base elements. There are people who are going to know that that means this is a vector space with 3 base elements. Okay, right, so that's just another way of making one of these things, which is a nice alternative, I think. So What about making a birthday magic square with more magic? I really wanted to talk about this. I thought you were going to give me a hard time about this, and you didn't. I don't know. You didn't even notice. So if you go back to like the original Euler square that I was showing off, it looked like this. So this is A, B, C, D's and 1, 2, 3, 4s, right? Just plain simple Euler square. Now, automatically you get all this magic total stuff, right? So the rows and the columns and the diagonals and the quadrants, because they're going to have A, B, C, D and 1, 2, 3, 4. All the quadrants, middle numbers follow the same, these broken diagonals. So there are some groupings that don't have that magic total. And you can see them when you look at the structure of it. So you don't have, was it these 4 numbers? Don't have it because it's not A, B, C, D. I've got C, D, C and D. So yeah, then you're missing out on the magic total then. It's not guaranteed, it's not automatic. And I talked about broken diagonals as being 2 numbers and 2 numbers. But what about this as a broken diagonal? These 3 numbers here and this number here. Think of it like a wraparound. So imagine the top is wrapping around to the bottom and the left is wrapping around to the right. Some people will know this as a torus, right? A donut shape. So the top is wrapping to the bottom, the left is wrapping to the right. It's a magic square on a torus. So if we had that, then this would be a diagonal on the torus. We would have like groupings of 4 that would work here, like these 2 numbers would be touching these 2 numbers, so that would be a grouping of 4. But there will be some that won't work as well. So yeah, can we make some of these diagonals on a torus work? It's called a most perfect magic square. It has even more magic. It has magic everywhere. Most perfect magic square, sometimes called pan-diagonal. So all these broken diagonals work. Sometimes called diabolical, which is a fun word. So yeah, can we make a most perfect magic square? Well, not automatically, not from the Euler square, but I do have now some conditions that I want to satisfy. I want this broken diagonal here, and this one down there, to add up to the same total as one of these rows. So what have I got? I've got B plus 2, A plus 2, A plus 3, and B plus 3. And I want that to add up to that. So, in other words, I can set myself up some conditions. I'll just write it out. If I do that broken diagonal I've just described, it would be 2 lots of A, 2 lots of B, and 10. That's that broken diagonal here, with this number here. And that's going to be equal to one of the rows. That's what I want, which is A plus B plus C plus D. Write that in. Plus 10. Which is fortunate, the 10s are going to cancel out. Actually, you can cancel out a few other things, and you're going to have, this is the condition, A plus B equals C plus D. If you can choose A, B, C, and D, so it fits that condition, then you're going to get a whole bunch of extra magic, because that diagonal is going to work as well, and these other diagonals and these other groupings are going to work as well. I can show you what that is going to look like. So here is me doing exactly that, like the one I started with, where I did a magic square with consecutive numbers. I'm going to pick A is 0, B is 12, C is 4, D is 8. Now that condition is satisfied. A plus B is equal to C plus D, right? So that condition's been satisfied. I fill that in. Using my Euler square here, I'm going to use consecutive values 1 to 16. Magic total is still 34, but with extra magic. All right, so now I should be able to get 14 plus 2 plus 3 plus 15 equals 34. Yes, it is. But the other diagonals, like this 7 and 11 and 10 and 6, it's going to add up to 34. I can do the other ones as well. And some of those groupings that didn't work before, like this one here on the left-hand side, this 8, 11, 5 and 10, it's going to add up to 34. That is now a most perfect magic square. Still has that structure, but I've added that extra condition to make some of the extra magic work. Okay, so if I look at the most generic version of the Euler square, and I say, oh, well then how can I make this? pan diagonal, most perfect. So this was the magic square with W, X, Y, and Z instead of numbers on the top row, and everything else filled in. Still an Euler square. I'm going to have to set up some conditions again. I want this diagonal now, with this number, to be equal to one of the rows, which is what? B plus X, A plus X, A plus Y, plus B plus Y. And I want that to equal one of the rows. Let's do it. So I can just write this in. Let's write that condition out. I've got B plus X, A plus X, A plus Y, B plus Y. I've got 2 lots of A, 2 lots of B, actually 2 lots of X, and 2 lots of Y. And I think, yeah, that's going to be adding up one of those diagonals. And I set that equal to one of the rows. Tell you what, actually this is the nicest way to do it. Instead of just writing that out, I'll just call it T for total. This is going to be the easiest way to do what I'm going to do next. So that diagonal is going to be the magic total. So this is what I can learn from that. I can learn that A plus Y is equal to, just rearranging what I've just written, T divided by 2 minus B plus X. I'll show you what I've just done there. So this is what I've got. This is just me taking that and just rearranging it a bit. So I've halved it and then I subtracted B plus X. But I've written it in that form because you actually discover something in that form. A plus Y is actually that cell there. A plus Y is that cell. And that is equal to the total divided by 2 minus B plus X, which is that number up here. Now your total isn't a choice. So imagine you're putting a birthday up here. Your total is no choice. B plus X is no choice. That was where you put your month. That's not a choice. That's not a choice. A plus Y is not a choice. That is forced on you. That entry there, that number, is already done before you even start making the magic square. That is a forced number, which means it could be, and you never know, it could be negative. It could be a fraction, especially with this T divided by 2. And there's nothing you can do with it. If you want this to be pan diagonal, if you want it to be most perfect, that's the value you have to put there. So if I do the exact same thinking with the other broken diagonals, let's do this broken diagonal, or this broken diagonal, or whatever I've missed, this broken diagonal. If I do that, I get 4 conditions. I'll show you what they look like. Looks like this. So this is me trying to make my diabolical magic square. And these are the 4 conditions I've got from those diagonals. If I want them to be equal to the total, this is what I get. A plus Y, which is what I've just shown you, is forced. It's the total over 2 minus the month. B plus Z, which is this here in the 3rd row. T over 2 minus the date. This one here in the 3rd row, C plus W, it's half the total minus the year. And D plus X, which is also in the 3rd row, it's half the total minus C plus Y, that is the century. All those choices are forced. That whole 3rd row is forced on you before you've even made any choices for W, X, Y, and Z. Yeah, so that's all forced. This is all about making the pan diagonal square. Now you get to make a choice. Now you can choose W and X, but that's it. Because when you choose W, Y is forced on you as well. So Y is a forced choice. It's A plus Y, which we now know is down here, minus A plus W, which we now know is up here, plus W. And if I choose a W, that determines Y. So Y is chosen for you. And if I choose an X, I get the same sort of thing for Z. Z is equal to B plus Z, which has been forced on you, minus B plus X, which is forced on you, plus X, which is a choice you've just made. And now Z has been determined. It's all determined for you. So you get, it's a lot more restrictive, which maybe is not surprising. So the more you expect the magic square to do, the more restrictive these choices are going to be. So let me show you what these look like. Maybe I'll show it to you like this, yeah. So let's do Euler, and let's try and make him a most perfect magic square. That's his birth date, 15/4/1707. That adds up to the birthday total, which is 43, right? That's forced on me, that's automatic, which means automatically that whole third row is made for me. That comes from those conditions there. So that whole third row, and you'll notice they've got 0.5s in them because this is an odd number, because I've got t divided by 2 in here. So now I've got, what, 4.5, 14.5, 6.5, 17.5. That's forced on me because it has to be to make this diabolical. Y is forced on me as well. That's 2.5. If I make a choice, W and X, I choose W to be 0. Let's keep it simple. And X to be 1. Y and Z forced on me as well. 2.5 and 3.5. Yep. And now you fill in the rest. You fill in the rest using the Euler grid here. Yep. And this is what it looks like. This is, but it is, most perfect. This is what you get. So there's your birth date, adds up to 43. All the rows add up to 43. Look at these. So those are all your halves there. This turns out into a row of halves as well. And then the other row there. But yeah, if we add up the diagonal, if we add up the 4 corners, if you add up all these groupings of 4, if you put this on a torus, you get a whole bunch of magic totals adding up to 43. So yeah, a lot more restrictive. It would be really nice, especially if you've got a birth date or birthday total that's even. If that's even, then those are going to be integers. That's going to be nice for you. They might include repeats. They might include negative numbers. So those are still forced on you. You can't avoid it. Now, what about doing it in an alternative way? So instead of doing it with the generic square, I do it as my kind of vector space version of this, which is this. So starting with this square. So if I start with this square, this is what I would get. So this is date, month, century, year. This is century, year, date, month. And then look at the third row. T over 2 minus century, T over 2 minus Y, T over 2 minus D, T over 2 minus month. And the fourth row, T over 2 minus date, T over 2 minus month, T over 2 minus century, T over 2 minus Y, the year. So that's your starting square. Then this is your base elements. So you could set W to equal 1 or X to equal 1. You'd get these 2 base elements this time. That's because Y's and Z's are chosen for you. So this is with W equal to 1 and this is with X equal to 1. That's your 2 base elements there. So this is what you get. Zeros in the top row. 0, 0, 0, 0. Minus 1, 1, minus 1, 1. 0, 0, 0, 0, 1, minus 1, 1, minus 1. This is the other base element, very similar. In fact, if you add those 2 together, they cancel out. They give you zeros everywhere. To put it another way, this is minus of this. So actually, you only need 1 base element. Just add copies of that. So if you just add some multiple of that, positive or negative multiple of that, you can generate all the birthday magic squares that you want. Using this as your starting square and then adding multiples of that. And you could do that yourself if you would like to do it in that format. So that is how you can make a most perfect magic square. And you can make one of those for yourself as well. Now, Euler squares, pretty great. You can use an Euler square to make a magic square of other sizes. You can make a 5 by 5 magic square in the same way with the Euler square. You could make a 7 by 7 magic square, or an 8 by 8, or a 9 by 9, or 10 by 10. Some of those are harder than others, but you can use Euler squares to make any magic square that you want, and it will have a whole bunch of magic properties. You can't make a 6 by 6. There is no 6 by 6 Euler square. It doesn't exist. It's impossible. It doesn't exist. So you can't use it for that. But there does exist and they do exist, 6 by 6 magic squares, which shows that Euler squares are magic squares. Not all magic squares are Euler squares. Yeah, so there's more to it than this. There are other things you could do. If you get into magic squares, there are other ways of making magic squares. And that's what you would have to do for a 6 by 6, which is perfectly possible. You can make 6 by 6 magic squares if you want. I'll just show you an example of that with the 4 by 4 though. So this is a 4 by 4. It's still going to be a magic square. Well, it will be, but it's not an Euler square. So I've got repeats. I've got repeats in the rows. See, I've got A's and B's and A's again. And I've got repeats here in the columns with the numbers. I've got 4s and 1s repeating in the columns. So you're not going to get an automatic magic square. You can make that a magic square though, by, like I was doing before with the diabolical most perfect magic squares. I'm going to have to set up my conditions. Right? I want, let's say, this is my main diagonal here, which does have the Euler property. It's got A, B, C, D, and 1, 2, 3, 4. And I want this row set to equal that diagonal, which gives me that condition. A plus B equals C plus D. Sounds familiar? Very similar. But it's not an Euler square. So if you set it now with that condition, yes, that row will add up to the magic total, which is given by that diagonal. You will get a magic square, and here is an example of me doing it. This is like one of the examples I showed you before, but remember with this condition, so I've got A equals 12, B equals 0, C equals 4, D equals 8, and I filled in this grid using those values. I've got a magic square using values 1 to 16, consecutive values, with all the magic properties like it should have, rows and columns, diagonals, and other things as well. But it's not an Euler square. And I've highlighted at the bottom here, don't know if you can see it, it's in green, 15 and 14 down there at the bottom. That's kind of special. Why? If you've looked into the history of magic squares, if you ever look into the history of magic squares, you will come across this square I've just made, because it is used in a famous piece of art. It's made by a German artist, I believe, called Albrecht Dürer, who made a piece of art in 1514. I'll show you this, which has a magic square in it. Let me go to my browser again and show you this picture. Here we go. Here it is. It's called Melancholia. Melancholia I, Melancholia 1. And it involves this figure here, which is meant to be representing melancholy. And she's surrounded by instruments of mathematics. She's got some sort of polyhedron there, some strange polyhedron here. She's holding a compass. She's got a sphere down here at the bottom left. And then here, up here in the top right here on this building is a magic square. It's the one I've just shown you, using all the consecutive numbers, all these magic totals. 1514 was included there on the bottom row because this piece of art was made in 1514. This is made in 1514, right? So it's kind of clever, right? And kind of special for that reason. And I believe it's like the first time a magic square was used in a piece of European art. Of course, you can always look at other countries. Magic squares come from other countries as well. But this was kind of bringing this idea into Europe, and then other people have played with it since then. So that's kind of special. Okay, that is, I think, enough about magic squares. And now hopefully you'll appreciate why I don't try and put in everything I know into one video. I'm going to finish. I hope that gives you some ideas. Let's finish with something nice. Let's finish with some of your comments, some of the things you said just about the main video, which was sort of the basic idea of how to make one of these birthday magic squares. So I've got some of your comments here. So I've got Matthew here. Matthew Ellisor said, great one. My thoughts first go to how could this be worked into a Brian Brushwood style performance. So Brian Brushwood is a magician on YouTube who is one of my YouTube friends, and he would love this. You're absolutely right. He would love this. I must share it with him so that he knows this. Yeah, it's right up his street, this. So I must share him that video. I've got a comment here from, now let's see, Old Cow BB. Okay, 90% of mathematical methods are called Euler's method. That is true. That is a true fact. You're absolutely right. I agree. Yeah, Euler's got his name on everything. Clever guy. What have I got here? Yeah, I've got a comment here from Peg Y. This is so cool. Thanks for sharing the secret. This gives me a month to practice before my sister's birthday. Then I can firmly cement my standing as the nerd of the family. Great. Perfect. That's exactly the sort of thing I wanted. I've got a comment here from Ken Warder. Mathematics and mathematicians are way cool. His words of Ken Warder, not mine. Only mathematicians can have fun with numbers such as this and sometimes get paid for doing such things. Yeah, well, some of that is true. I won't tell you which bits of that is true, but some of it is true. Constantine, super cool. I'm going to make a magic calendar which generates a new square for every day. Like that. That's a nice idea. I've got, how am I going to pronounce this? IOWYYN? Ewin? I've got a family member who's going to find this beyond exciting. I'd forgotten about this, so it's a great reminder to get one created now. Yeah, even if you did know about birthday magic squares, hopefully I've reminded you that they exist as well, which is always nice. Now I am going to finish, but I'm just going to finish with like a little plug. A plug for things I'm doing. This is a plug of something I've been making on someone else's YouTube channel, and it needs more love and it needs views, I guess is what I'm saying. And it's not just me, so some of your other favourite mathematicians on YouTube have been doing this as well. So I'm going to show you what this is if I flip over to that browser again, which is this, yeah. So we were asked, and you may recognise some of the faces there, we were asked to make some videos for Further Maths Wales. So Further Maths Wales is kind of encouraging GCSE school students, particularly though in Wales, to study maths at A level, to go further with your maths. So we were asked to make some videos specifically to be shown in classrooms to GCSE age school kids, so 15, 16-year-olds, which showed maths that they are doing in GCSE level maths, but showing some interesting application of that or some interesting thing about it. And yeah, you may recognise some of these faces. We've got Katie Steckles, we've got Ben Sparks, we've got myself there I am. There's James Grime and Zoe Griffiths there, who some of you might know. And I believe there's going to be more videos coming as well. And just to point out that this is made with a specific purpose, to be shown in classrooms for school kids. So it's not exactly like a YouTube video that we might make on our own channels. So, just appreciate it's going to be slightly different, but we would like this to be a success. So it is made for Further Maths Wales. That's why there's two versions of each video, one with Welsh subtitles and one without. So you'll see two versions of each one. For myself, I did a video about finding the horizon. So that uses how ancient people in ancient times used trigonometry, your basic school level trigonometry, to work out the size of the earth. How big is the earth? How far is the horizon? So that's what that video is about. And another video there about maths to share secrets, which is about how you could have, say, like a bank vault, and you want two people to agree and cooperate before they can open that bank vault. So like they both got like a key each, and they have to cooperate and use both their keys to open up the bank vault. But how could you do that for like two people? How could you do that for 3 people, 4 people, that kind of thing? Mathematical way of doing that. It's called secret sharing. I actually did a video about, do you remember I did one about codes with the Barbie typewriter? And I was hinting that I was going to do one about codes. Someone said, oh, is it going to be about secret sharing? And I did see that comment, by the way, and I went, oh, I'm doing it for Wales people. So I did know that that was coming, so now you can watch it. Especially that person who wanted to see me do something about secret sharing. It's pretty cool. So now you can watch it there. You can see they don't have many views because they haven't been advertised, right? They're made for a niche audience and they've been advertised to that niche audience. But we also want it to look good, look like it's been a success, so that then we can make more of them. So if you go and watch them, then they have more views and it looks really successful. Then we get to make more of them. Right, there you go. So that's what we want. All right, I'm going to leave it there. Switch back to me. I'm going to leave it there. I'll put the link to what I've just plugged there, the Welsh thing. I'll put a link to Christian's birthday magic square generator there. I made a spreadsheet. I made an Excel spreadsheet so I could start playing with these a bit easier. I was doing it pen and paper until there came a point where I made so many of these. I went, I'll just turn this into a spreadsheet. So maybe I'll just put a link to that as well, so you can play around with the values and things. So I made a spreadsheet, and I made one for making most perfect magic squares too. So I'll combine those, and you can just flick between the sheets on the Excel spreadsheet. Right, and I think I'll leave it there. Wikipedia has loads more information if you want to know more. I'll leave it there. I probably could end every video with that. And Wikipedia has loads more information if you want to know more. I will end it with that. I don't have a catchphrase to end these follow-up videos. That might become my catchphrase. So I will say goodbye for now. Be well. Take care. See you in the next video. Bye.